Have you ever really thought about what's going on inside that little power adapter you plug in for your phone? I mean, the power that comes out of the wall socket is totally different from what our devices actually need to run. Well, today, we are going on that incredible journey from AC to DC. Let's jump right in.
You know, it seems so simple, right? You just plug in your charger and boom, it works. But there's this really fascinating conversion happening behind the scenes. The electricity in your walls is this wild, alternating current. But the power your gadgets are thirsty for is a calm, steady, direct current.
So this is the big challenge we need to solve: how to get these two totally different types of electricity to play nice. You've got alternating current, or AC, on one side, and on the other you've got direct current, or DC. And honestly, they're just not compatible on their own. Okay, think about it like this. The AC power from your wall is like a wave in the ocean, constantly surging forward and then pulling all the way back. But your phone's battery, it needs a calm, steady river of power that only flows in one direction. That's our DC. So the million-dollar question is, how do we tame that chaotic wave and turn it into a smooth flowing river?
This is where our hero comes in. It's a device called a rectifier, and its job, while it sounds simple, is absolutely critical. Its whole mission is to grab that wild two-way AC current and force it to flow in just one direction, creating the DC output we need.
So let's start with the most basic version of this converter, the halfway rectifier. You could call it the first attempt at solving the problem. It's simple for sure, but as you're about to see, it's not exactly what you'd call efficient.
All right, I know this might look a little complicated, but don't worry about all the math for now. Just focus on that main circuit in the middle. The real magic ingredient is that little component that looks like an arrow hitting a wall. That's a diode. A diode is basically an electrical one-way street. It lets current flow in the direction of the arrow, but it completely blocks it from coming back the other way. And for this simple setup, we just need one of them.
So as that AC wave swings into its positive half, the current is flowing in the same direction as our diode's arrow. We call this forward biased, and the diode just opens up the gate, letting that pulse of energy go right on through to the output. You can see it right there on the graph. That positive hump of the wave makes it to the other side.
But here's the problem. When the AC wave tries to swing negative, the current tries to flow backward, against the diode's arrow. We call that reverse biased, and the diode immediately slams the gate shut. Nope, not happening. No current can pass. And the result, as you can see, is that we get these little positive pulses of DC, but we've completely thrown away the entire negative half of the power. It's just gone.
And this number right here just perfectly shows the problem. The efficiency is a pretty terrible 40.6%. That means we're wasting almost 60% of the energy from the wall socket. That's just not going to work. There has to be a better way to do this.
And of course, there is a better way. Engineers came up with a much smarter solution, the full-wave rectifier. And just like the name says, its goal is to capture the entire wave, not just half of it.
Now, this circuit might look a little more intimidating, but the key changes are actually pretty simple. First, you'll see we now have two diodes instead of just one. And second, that transformer on the left has a special center tap, that little wire coming out of the middle. That tap is the key. It splits the AC wave into two halves, so we can send the positive part to one diode and the negative part to the other.
Okay, so here's the really clever part. When the AC wave is positive, that first diode opens up and lets the current through, just like before. But when the wave goes negative, the second diode takes over. It opens its gate, catches that negative part of the wave, and actually flips it, so it also flows out in the positive direction. See? No energy gets wasted.
And I mean, the results really speak for themselves. Just look at this comparison. Our efficiency literally doubles, jumping all the way up to 81.2%. And because we're grabbing both halves of the wave, our output now has twice as many pulses. This is a huge improvement.
So we solved the efficiency problem, which is awesome. But we've kind of created a new one. Look at that output. It's like a series of hills, right? Yeah, it's all flowing in one direction, but it's still a really bumpy, pulsating current. A sensitive computer chip can't run on that. It needs a perfectly smooth flat line of pure DC.
And that brings us to the final and absolutely critical step in this whole journey, smoothing things out. To get from this bumpy mess to that pure DC we want, we need to add one more thing, a filter.
The most common way to do this is with another simple little component, a capacitor. You can see it labeled with a C in the diagram. Notice how it's placed right across our output.
It basically creates a little reservoir for electricity right before it leaves the circuit. And its placement here is the key to how it works its magic.
So think of this capacitor as a tiny, super-fast water tower. As each pulse of DC comes rushing through, the capacitor charges up, storing energy right at the peak of the hill. Then, as that pulse starts to fall, the capacitor instantly releases its stored energy, filling in the valley that would have been there.
And here it is. This is the payoff. Just look at the difference. On the left, you've got the bumpy before picture. That's the output from our full-wave rectifier. Then on the right, the after picture, once we add our capacitor filter. Those valleys are all filled in, creating this beautiful, nearly flat line of smooth, stable DC power. This is the clean energy that our electronics can finally use.
So let's just quickly recap that whole journey from your wall to your device. First, we use a rectifier, our electrical one-way valve, to turn that messy AC into one-directional DC. Second, we learn that a full-wave rectifier is way better because it cleverly captures both halves of the AC wave, doubling our efficiency. And finally, we add a capacitor filter to act as a little reservoir, smoothing out all the bumps into the clean, stable power that every modern gadget we own relies on.
And there you have it. From a chaotic wave of alternating current to a steady stream of direct current, all thanks to just a few simple components working together perfectly. This basic principle is hiding inside almost every single power adapter you own. It really makes you wonder, right? What other seemingly simple ideas form the invisible foundation of our modern world?